the magnetic potential energy stored in an inductor is equal to 1/2 times the inductance of the inductor times the square of the current passing through the inductor. Using this, we've shown that the magnetic energy density per unit volume in a magnetic field is given by 1/2 times the magnitude of the magnetic field squared divided by the permeability of free space. Let's apply these results to an example. A 10.0 microhenry inductor is 5.7 centimeters long and 4.0 millimeters in diameter. Suppose it carries a 0.10 amp current. What are the magnetic energy stored in the inductor, the magnetic energy density, and the magnetic field strength within the inductor? Let's begin with a sketch. Here we have an inductor. This inductor has a length L. This length is given to be 5.7 centimeters. This inductor also has a diameter, and that diameter is given as 4.0 millimeters. This inductor carries a current. I'm going to indicate the current that it carries from left to right. This current is coming towards us at the top of this solenoid and going away from us at the bottom of this solenoid, which we're using to represent the inductor. And we're told that the magnitude of the current is equal to 0.10 amps. We're also told that this inductor has an inductance of 10.0 microhenries. Using this information, we first have to determine the magnetic potential energy stored by the inductor. Well, this inductor, having a current passing through it, means that there is a magnetic field within the inductor. And based off of the orientation of the current, and after having applied the right-hand rule, we would determine that the magnetic field is going to the right. That magnetic field stores magnetic potential energy. And we've shown that the magnetic potential energy that is stored by the magnetic field is given as 1/2 times the inductance of the inductor times the square of the current passing through the inductor. Well, here we have everything we need to determine the magnetic potential energy. We have the inductance, which is equal to 10.0 microhenries. And we have the current, which is equal to 0.10 amps. When I plug this into my calculator, I get the value of 5.0 times 10 to the minus 8 Henry amp squared. Well, we typically express energy in units of joules, and here we have units of Henry amp squared. So as a reality check, let's just convert these units to see if we end up with joules. We're looking for joules, and we need to determine what Henry amp squared is in terms of joules. Well, we know that 1 Henry is equal to 1 Tesla meter squared per amp. And then we have the amp squared, but an amp in the denominator cancels an amp in the numerator. We know that a Tesla is equal to a Newton per amp meter, and we have a meter squared and an amp. So a amp in the numerator cancels an amp in the denominator, a meter in the denominator cancels a meter in the numerator, and the units end up being a Newton meter And we know a Newton meter is equal to a joule. So with that said, we can say that the magnetic potential energy stored by this inductor is equal to 5.0 times 10 to the minus 8th joules. Now we have to find the energy density of the magnetic field within the inductor. Remember, energy density, we'll use a lowercase u, is equal to the potential energy per unit volume. Now, previously, we derived an expression for energy density in terms of the square of the magnetic field and the permeability of free space. But if we go back to basics, we could say that the potential energy is just equal to 1/2 Li squared, which we have all of those parameters, and then this is going to be divided by the volume of the solenoid. Well, the solenoid occupies a volume equal to a volume of a cylinder of radius A and length L. So the volume that we're going to divide by is going to be equal to the product of the area of a loop and the length of our solenoid. So this is just 1/2 the inductance times the current through the inductor squared, divided by the area of a loop, which is pi times the radius of loop squared, and a radius is just a diameter over 2, quantity squared, times the length of our solenoid. So this then is just 1/2 Li squared. Now the inductance we already know is 10.0 times 10 to the minus 6 henries. The current is 0.10 amps. This quantity is squared. And this is divided by pi times the square of the diameter, which is 4.0 millimeters. And this is going to be divided by 4 times the length of the inductor, which is 5.7 centimeters. Now, we already know that a Henry amp squared is going to be joules. So we have joules on the top. And notice we have a meter cubed on the bottom. So that meter cubed on the bottom and the joules on top gives us our joules per meter cubed, our energy density. And when we plug this into our calculator, we get that the potential energy density of the magnetic field is 0.070 joules per meter cubed. So we now know the magnetic potential energy stored by this inductor. We know the energy density of this magnetic field within the volume occupied by the inductor. Using this information, we now have to determine the strength of the magnetic field within the inductor. To do that, we could turn to the expression that we found for the magnetic potential energy density in terms of the magnetic field, which is equal to 1/2 times the square of the magnitude of the magnetic field divided by the permeability of free space. We could rearrange this to isolate the magnetic field on one side of the equality. And when we do this, we get that the magnetic field is equal to the square root of 2 times the permeability of free space times the energy density of the magnetic field. Well, this is just the square root of 2 times the permeability of free space times the expression that we got for the energy density of the magnetic field, which is equal to 1/2 times the inductance times the square of the current through the inductor divided by the area of a loop of the inductor times the length of the inductor. This then is 2 times the permeability of free space, which is 4 pi times 10 to the minus 7 Tesla meter per amp, times 1/2 the inductance of our inductor, which is 10 microhenries, times the current through our inductor squared, which is 0.10 amps quantity squared, divided by the area of our inductor. The area of our inductor is the pi times the diameter over 2 quantity squared. The diameter was 4 millimeters over 2. This quantity is squared. And this is times the length of our inductor, which is 5.7 centimeters. All underneath a square root. You might be wondering, why are we plugging all of these values back in when we already found the value for the magnetic potential energy density for our problem? Well, one big reason for it is I never like to use rounded results. Since we expressed our previous results given its appropriate significant figures, that involved rounding. And if we reuse a rounded result, that'll just give us a result that is potentially a little bit off because we're introducing error. So I'll always go back to the original quantities and express our answer in terms of the original givens to minimize any kind of rounding mistakes. Now, I do recognize that this is exactly what we've had before, and if we wanted to, from here, we could do some simplifications. After doing a unit check and then plugging this into my calculator, I get that the magnitude of the magnetic field within this inductor is equal to 4.2 times 10 to the minus 4 Teslas.